Good morning. So the topic for the day is moment about a point and an axis. And I am E. Ilavenil, Assistant Professor, Department of Mechanical Engineering, Thandai Periyar Government Institute of Technology, Vellore. So moment about a point. Of course, we have seen quite a deal on moment about a point. So normally the moment that we have seen so far has been moment about a point only. So as already seen, moment m is equal to r cross f. Of course, here I have to remind you that once again the letters have been made bold in order to denote that they are vectors. So we should say m vector is equal to r vector cross f vector. Okay. So the value of the moment here is hence obtained in a determinant form. So this is the determinant form. So with r vector given by rxi plus ryj plus rzk and the force vector fxi plus fyj plus fzk, we get moment vector m is equal to I, j, k, rx, ry, rz, fx, fy, fz in this determinant form. Okay. Of course, we all know how a determinant should be expressed. So we have an analytic expression for this determinant form, which as a single expression can be given by ry fz minus rz fy into I plus rz fx minus rx fz into j plus rx fy minus ry fx into k. Actually, it is this form that we have already studied when we studied about the vector operations. Okay, the cross product and all we have seen in yet another lecture. So there we have seen a very similar expression, but instead of moment, instead of r vector and f vector, we have gone for some random vectors for the understanding purpose. So it is this expression that we usually get, that which is converted into the determinant form. So here the determinant form would be easy and convenient for remembering and using rather than remembering this full expression in the right sequence. So when you try to remember this, you might forget first or y f z or f y r z, or whether it is z and x or whether it is x and y. So in this portion there may be confusion. Again, to avoid confusion, we have other ways like take I into j equal to k, j into k equal to I, and all these types of expressions we can use, and each and everything we can separately, independently calculate and finally come to the same expression. However, that would be time consuming, and hence usage of determinant form would be very easy. So we see a small example. So let the force vector be F is equal to 3i plus 5j minus 2k newtons. Let the position vector be R vector is equal to 2i minus 3j plus k meters. Then the moment vector is given by m vector is equal to r vector cross f vector, which may be obtained through the determinant expression. So the determinant expression is shown here. So that is I, j and k, 3, 5, minus 2, 2, minus 10, minus 1 as shown in the expression in determinant form. So this should be expanded as shown here. So m is equal to 5 into minus 1 minus 10 into minus 2 into I plus minus 2 into 2 minus 3 into minus 1 into j plus 3 into minus 10 minus 2 into 5k. So here m vector is obtained as minus 25i minus j minus 40k Newton meters, which is the answer. But we can also obtain its magnitude, which is given by m is equal to square root of minus 25 square plus minus 1 square plus minus 40 square. Instead of square root, here the expression is shown as whole power half, which is nothing but square root. So this gives us the answer as 47.1805 Newton meters. Of course, as told earlier, we can also go for the direction in the form of direction cosines, which is not going to be the purpose by which we are going through this. It just is understood that we obtain it with magnitude and direction in vector form, or we just obtain its magnitude as a single scalar value. Okay. So next we are going to see about moment about an axis. So as told already, moment about a point is also moment about an axis. Okay. So here rotation or rotary effect about an axis is more specific than moment about a point. Actually, moment about a point itself is a moment about a particular axis, that is about an axis perpendicular to the plane containing the force and the position vectors passing through the point mentioned there. Okay, so by default it finds out which axis it is going to rotate about, but what we refer here is about any random axis. So original moment is with respect to some axis, but this rotary effect is also pronounced about some other axis which may be of a lower magnitude, but still it can create rotary effect about some other axis. So this moment about an axis refers to the moment about any specified axis with any orientation. So this specifies the component of moment that tends to rotate the body with respect to that particular axis, maybe a lower effect. This means that moment about an axis is smaller than or equal to the moment about a point, and that is projection of that moment in the specified axis. So we have already seen about projection on a particular axis. It is nothing but dot product. Okay, projection of any vector about another vector or another axis is given by the dot product of the vector and the axis unit vector. So here mq, that is moment about an axis q, is equal to moment vector dot q vector, which is unit vector along q axis. So since this is a dot product, this mq is not a vector, it is a scalar. Dot product, in other words, is referred to as scalar product. So this mq, a scalar value, is obtained by dot product of two vectors, out of which one is unit vector, which is the axis direction. So since it is dot product is commutative, it is m dot q or q dot m. Okay. So this is what we obtain about that axis when we know the moment about a point. So finally, as we know that moment vector is equal to r vector cross f vector, this q dot m is equal to q dot r cross f. So this is a triple product, vector triple product as we say, which does not specify the direction because it is a scalar. So it is a scalar quantity and it will not show any direction, but we know the direction. How? We are only obtaining the component along the q axis. Already the direction is known. It is q axis. So it is about the q axis. How much rotation we are getting, that is only we are finding out, which means it is going to rotate in a plane perpendicular to the q axis where you will have the rotary action. So this can again be expressed easily and conveniently as a determinant. So here this determinant form is qx, qy, qz, rx, ry, rz, fx, fy, fz. So as you take the determinant here, there is no ij, k. So finally it is going to be a single numerical value. Of course, when you substitute everything by the corresponding numbers, we are going to get only a single number value finally. So we are going to just obtain a number, a numerical value, which is going to give the moment about an axis, and the direction as specified earlier, we already know the direction, and that is the direction in which we are going to have the moment, that is about the q axis. So this is what is about moment about an axis. So not so often that we are going to get a moment about an axis, but whenever a particular system has a possibility of rotation only about a particular axis, in whichever direction we produce a moment, only the component along that particular axis we are going to have a rotation in dynamics. However, this is statics, which means in whichever direction you apply a moment, what we are going to get is a reaction moment or reaction couple only about that q axis. That's what it happens in statics. So with this we stop here. So we have seen about moment about a point and moment about an axis and their corresponding comparison. Okay, so with this we stop here and we'll see in yet another lecture. Thank you.